In this video, we're going to be talking about motion problems, in particular distance equals rate times time problems. And these types of problems can end up as linear equations, quadratic equations, or in this case today we're going to be talking about rational equations and some of the keywords that tell us that it's going to be a rational equation. Starting with this example here on the left, it says Nancy drove her car to Cleveland while Patty drove her car to Columbus. Nancy drove 360 kilometers while Patty drove 280 kilometers. Nancy drove 20 kilometers per hour faster than Patty on her trip. What was the average speed in kilometers per hour for each driver if they traveled the same amount of time? So this same amount of time is going to be important. It tells us that this problem is in reference to time. So we should probably solve this equation, distance equals rate times time, for time. So I'm going to go ahead and divide both sides by rate. And that means that time is equal to distance divided by rate. That's going to be important for us. Now, just like our motion problems when we solved them in previous sections, we're going to set up a little chart. So I've got Nancy, and I've got Patty, and we're going to need to know about each one of their distance, rate, and time. Alright, and we begin to fill in our chart. So, Nancy drove 360 kilometers. That is her distance. And Patty drove 280 kilometers. So we know Patty's distance. Now what we don't know is really their rate or their time. But we do know something about the rates. Nancy drove 20 kilometers per hour faster than Patty. So that means that we don't know anything about how fast Patty went, and she's going to be our first variable. We know nothing about her rate. We know Nancy's rate is 20 miles per hour faster. So whatever Patty's rate was, we want 20 miles per hour faster than that. Now, we also don't know anything about their time, but we really don't want to put in another variable here. Even though we have two equations and we'd have two unknowns, it's not going to work very well with time being another variable here. So what we can do is instead of writing another variable, we can use this. Time is equal to distance divided by rate. And again, this key here, same amount of time, tells us the problem is all going to be in respect to time. So we take each one of their distances and divide it by their rate. So that's what I'm going to put in the time box. Nancy's time would be the 360 kilometers divided by her rate, which was r plus 20. Patty's time was the distance divided by her rate. And since they are the same time, these two boxes are equal. Nancy's time will equal Patty's time. And now I have a rational equation. And we know with rational equations we need to get a common denominator. So r and r plus 20 are different factors. I'm going to go ahead and multiply the left-hand side by r. So now I have r plus 20 in the denominator. I'm going to multiply the left-hand side by r plus 20. And now again I have r plus 20, r plus 20. Once the denominators are the same, we can clear out those denominators by multiplying each side of the equation by the LCD. And this leaves us with only what's left in the numerator. So I'm going to go ahead and simplify and take r times 360, which is just 360r, right? Multiplication's commutative. I'll distribute, So 280 times r plus 280 times 20, which is 5,600. I want to get all my r's on the same side. So we subtract 280r from both sides. And now I have 80r equals 5,600. Divide both sides by 80 to get the r alone. And r equals 70. And since this is in kilometers, it's in kilometers per hour. And the question is, whose rate is this? Well, r was Patty's rate. So Patty was going 70 kilometers per hour. And we want to know Nancy's speed. Well, hers was 20 miles per hour faster. So Nancy was going 90 miles per hour. Or sorry, kilometers per hour, not miles. And there we have both of them. All right, let's look at another type of problem. This one says, Bill can ride his bike 3 miles per hour faster downhill than on level ground. His bike ride to Salt Lake Community College is 3 miles on level ground and 2 miles downhill. It takes him a half hour to get to school. How fast does he ride his bike? All right, so we're going to do the same thing. We're going to make a chart about his downhill experience and his was on level ground. Distance equals rate times time. And now we've got our chart, and we fill in what we know. So he can ride his bike 3 miles per hour faster downhill than on level ground. So we don't know anything about his speed on level ground. That's going to be our rate, R. And then he can ride 3 miles per hour faster downhill. So whatever his rate is on level ground, plus 3 miles per hour faster. That's going to be his rate for downhill. Then it says his bike ride is 3 miles on level ground. So distance is 3 for level ground, and 2 miles per hour, just 2 miles downhill. So his distance downhill was 2 miles. Now the only thing we know about the time is that the whole trip takes him 1/2 hour. So that means that this time plus that time equals the 1/2 hour to get to school. So again, I need to know more about the time, and I don't. So again, I'm going to use that fact that time equals distance divided by rate. So instead of adding another variable to my equation, I use the distance box divided by the rate box, and that will be the rate for downhill. So 2 divided by r plus 3. For level ground, I take the distance and divide it by the rate. So 3 divided by r. Now, instead of setting them equal like on the previous example, we're going to add them up. This time plus that time has to equal the total time to get to school. So 2 over r plus 3 plus 3 over r equals 1/2. Right? So time going downhill plus the time going on level ground has to equal his total time to get to school. All right. Same thing, I have a rational equation here. I need to identify the LCD. I notice that these are all distinct factors. R plus 3, R, and 2 are all different factors because there's nothing else I can factor out of them, and they don't look the same. So they're all different factors. So I have to use all of these when I make my common denominator. So my first denominator needs a 2 and an r. So 2 times r plus 3. whatever I do in the denominator, same thing in the numerator. The second denominator, r, needs a 2, and it needs an r plus 3. So now it has 2r, r plus 3. The last denominator on the other side of the equation has the 2. It needs an r and an r plus 3. Same thing in the numerator, r plus 3. Now all the denominators are like 2r, r plus 3, 2r, r plus 3, 2r, r plus 3. Once all the denominators are the same, I clear out those fractions or rational expressions by multiplying everything by the LCD, and they all divide out. The only thing I'm left with is the numerator. So now I have 2r times 2 is 4r, plus 2 times 3 is 6, times that r plus 3, which I'll distribute in a moment, and then 1 times r is r, times that r plus 3, and again I'll distribute in a moment. So now once I have my equation, I distribute to get rid of all those parentheses. 6 times r is 6r, 6 times 3 is 18, r times r is r squared, and r times 3 is 3r. I notice that this is not a linear equation. I have an r squared, not linear. So that means I need to get everything on one side and have it set equal to 0 on the other. So I need to move everything to the right to keep this r squared positive. So these two are 10r. So I'm going to subtract 10r from both sides. So 4r plus a 6r made 10r. I subtract it and move it to the right-hand side. I'm also going to move 18 to the right-hand side by subtracting it. What's left? Alright, so 10r minus 10r is 0, 18 minus 18 is 0. I have 0 on the left-hand side, r squared, and then 3r minus 10r is negative 7r, minus 18. My next step from there is to try to factor. Again, when it's not linear, get it on one side, try to factor. So I need factors of negative 18 that will add to a negative 7. I'm thinking 9 and 2, and for it to add to negative 7, the negative has to go with the 9. I factor into my two terms here. So leading coefficient was 1. I can go right into my sets of r minus 9 and r plus 2. I use the zero product property to set each factor equal to 0. r minus 9 could be 0, or r plus 2 could be 0, meaning r could equal 9, or r could equal negative 2. But negative 2 doesn't make sense for the context of our story, right? We're talking about a rate. We're not going to go at a negative 2 rate, so that is not our solution, and the rate is 9. So the question was, how fast does he ride his bike? He rides his bike 9 miles per hour. Alright, go ahead and try the two examples on the right-hand side. Okay, here we are looking at the next example that says a small airplane takes the same amount of time to fly 200 miles against a 30 mile per hour wind as it does to fly 300 miles with a 30 mile per hour wind. Find the speed of the airplane in still air. So I'm going to go ahead and make a chart here with the wind and against the wind. And distance equals rate times time. Right, now when we're talking about planes and wind and things, When we talk about the rate, we're not going to talk about just the rate of the plane. We have to talk about the rate of the plane plus or minus the wind. Because the wind is either helping you go faster or making you go slower than the actual rate at which you're traveling. So let's start filling in these boxes. So it's traveling 200 miles against the wind. So that's going to be 200 miles against the wind. And then it flies 300 miles with the wind. Then we're going to look at the rate. So it said against the wind of 30 miles per hour. So however fast that plane is going, we don't know. The wind is slowing it down by 30 miles per hour. We are fighting against the wind, slowing us down. When we're going with the wind, whatever speed that plane is going, the wind is pushing us along 30 miles per hour faster. Now, again, that key was this phrase, in the same amount of time. So these boxes of time, we're going to use time equals distance divided by rate. So 300 divided by p plus 30, and 300 divided by p minus 30, or sorry, 200. Since they are the same, that means they are equal. So the time with the wind equals the time against the wind. And then we've got our equation. 300 divided by p plus w equals 200 divided by p minus w. And then, again, we need to get a common denominator since it's a rational equation. There are distinct factors in the denominator. So on the left, we need to add p minus 30. And on the right, we need to add p plus 30, both to the numerator and denominator. Once the denominators are the same, p minus 30, p plus 30, p minus 30, p plus 30, we clear out those denominators by multiplying everything by the LCD. Now what's left is only the numerators. We've cleared out those rational expressions. I can distribute, so 300 times p is 300p. 300 times 30 is negative 30 is negative 9,000. Equal to 200 times p is 200p. 200 times 30 is a positive 6,000. I need to get all my variables on one side, all my constants on the left. This is linear. It's a linear equation. I do not need to factor. I just need to get p alone. Move the variables to the left, constants to the right. So I subtract 200p from both sides and add 9,000 to both sides. This leaves me with 100p equaling to 15,000. Divide both sides by 100, and p equals 150. That is the speed of the plane in still air at 150 miles per hour. Alright, the next problem. It says two automobiles going in opposite directions leave at the same time. Car A travels at 55 miles per hour, while car B travels at 75 miles per hour. So they're starting at the same place and then going in opposite directions. Now their distances are going to be different because one is traveling at 55 miles per hour and the other is traveling at 75 miles per hour. So even though they're traveling for the same amount of time, car B is going to end up going further because it's traveling faster, right? And that's all the information we know. So again, I'm going to fill in a chart. Car A, car B, and distance equals rate times time. Alright, we don't know anything about the distances of car A and car B. I'm just going to say distance 1 and distance 2, since they're different distances. And they have to be different distances because they're traveling at different speeds. And so car A was going at 55 miles per hour, while car B was going at 75 miles per hour. Now we don't know anything about their time, except for if they're leaving at the same time, and they'll reach 650 miles at the same time, that means they're traveling for the same time. So this is the same variable. They're leaving at the same time. At a certain point, they will reach 650 miles apart, but that will also occur at the same time. Now, looking at this, you might think, how can I solve this? I don't have enough information. I've got 1, 2, 3 different variables, but only 2 equations. And it's true. So distance 1 equals rate times time. Distance 2 equals rate times time. But I have one more piece of information. They're going to end up a total of 650 miles apart. So from one side to the other is going to be 650 miles total. That means that however far car A travels plus however far car B travels, they need to end up 650 miles apart. Well, distance 1 is going to be made up of 55t. That's what it equals. So instead of writing d1, I substitute in 55t. d2 equals 75t. So I replace d2 with 75t. And that still equals 650. Now I've got one equation and one variable. I can solve one equation with one variable. And you might ask, why is this in this section? I thought we were doing rational equations. And this one's here just to make sure you're not blindly regurgitating these types of problems. You need to break it down, think about what I know, what do I not know, what's in common, what's not in common, and be able to set up an equation from that. So do not get set in this pattern of only doing rational equations in the rational chapter and linear equations in the linear chapter. You need to be able to solve any kind of problem at any time. Alright, let's continue on. So one equation, one variable. I combine my like terms. 55t plus 75t is 130t equal to 650. Divide both sides by 650, and t equals 5. And that was 5 hours. Since it was talking about miles per hour, time is in hours. And there you have it. So I highly, highly recommend making these charts, filling in what you don't know, looking for key things. Like this problem was all in reference to time, their total time, or the same amount of time. That means I'm going to use this time equals distance divided by rate. But be careful not to get caught in the trap of thinking it's always going to be the same way every single time.